Good afternoon, everyone. It's 3 o'clock, so we should probably kick off. Thank you so much for coming. How many people were here for the previous session? Oh, okay, quite a few. Awesome. In which case, I will skip over this slide or mention very lightly. I'm a freelance consultant, blah, blah, blah. Most important reason for this slide is my contact details. So please get in touch if there's any questions, if I haven't explained anything. So this session, we're going to dive a fair bit deeper into some of the concepts within Kubernetes. In particular, we'll talk about scheduling, admission controllers, how we can extend Kubernetes, and we'll finish off with a slight change of pace, and we'll talk about some virtual node stuff and some service meshes, and hopefully demos. As I realized in my last session, I forgot to show you a video of the rolling updates. So apologies for that. I would have been way over time as well, but hey, if anyone wants to see that, I'm happy to share it with you. So what we're not going to cover is the fundamentals. Hopefully, if you needed to cover that, you would have been in the previous session. Even then, if you're still very new to Kubernetes, then the first 20 minutes, 30 minutes of this talk may be a bit too much, because you need to have kind of worked with it for a little bit to get a feel for what I'm talking about. I'm not going to deep dive into how we create custom controllers and operators. That's a big topic. That's a workshop in itself. And I'm not going to deep dive into service meshes. I will share a link to a video of a talk I did in Sydney last year where I do cover that topic. So time for you folks to do some work. So please put your hand up if you're using Kubernetes at the moment. Yep, hopefully I'd expect a lot more hands. In production? People using service meshes? No hands. You normally see one hand at least. Cool, okay. So pod scheduling. As I was saying to somebody earlier, this talk is going to be very dry, unfortunately. There's very little scope for humor when we're talking about scheduling pods. So I showed this slide in the last talk, and I said the scheduler's job is to run your pods, and we'll cover it more. So this is what this talk's going to be at, or this part of the talk, rather. When we look at scheduling pods, at a high level, it's actually quite straightforward. You create a pod. The scheduler detects that there's no node assigned to that pod, and it will assign a node. That's actually all the scheduler does. The scheduler doesn't run your pods for you. Its job is just to assign a node, and then other controllers kick in when they see the node assigned, and they take action. They do what needs to be done. So with the scheduling, you want to sometimes influence where your pods are being scheduled, where they're being placed. So why would you do this? So often, you may have a heterogeneous cluster. You may have some specialized hardware or some specialized software running in your cluster, and you need to make sure that certain things run in certain places. You may want to allocate resources to particular teams. If you're running a multi-tenanted cluster within your organization, or maybe you're a software as a service provider who's got multi-tenanted applications, you need to ensure that resources are specific to individual teams, groups. You may have regulatory requirements. So your regulator may say you must have certain software hardware running on for a particular application, and that may be expensive to have across your whole cluster or clusters, and therefore you may need to ensure that certain pods run on certain nodes. Sometimes your application architecture may require you to put components together, or more commonly, actually, you want to separate components. And we'll talk about why you might want to do this a little bit later. So we look at the ways we can influence the scheduling of pods. We have a node selector. We'll talk about all of these in a minute. We have node affinity and anti-affinity. We have node tainting and tolerations. We now can influence about pods themselves, pod affinity and anti-affinity. And then finally, the kind of nuclear option, a custom scheduler. So let's talk about node selectors. These are the simplest way of influencing where pods get scheduled. So essentially, we add a key value pair label to a node. We add a label. So in these slides, you're going to see K a lot. K is my alias for kube control. So kube control label node, give it the node name, and I give it a key value pair. So team equals foo in this case. Now my node is labeled. What I can do is I can in my pod specs or in my deployments, I can say that in my node selector, I can say I want the node that has the label team foo here. And then Kubernetes will basically schedule that pod on those nodes. Now, the problem with this is it's a little bit binary. If there are no nodes in your cluster with that label, your pods won't get scheduled. When you look at a node, there's actually quite a lot of labels on there. It's quite interesting to have a look sometimes. So you do a kube control describe node, and you can see some labels. I've truncated this, obviously, output. And you'll see a lot of the labels are actually added by your cloud provider. So we can see I've got an agent pool name. I've got some Kubernetes-related stuff. I've got this failure domain, which might be interesting. I've got some regions, and I've got some indication of the type of VM, potentially, and some of the storage indicators there. So I said node selectors were a little bit basic. They're a little bit crude. So what we can use instead is node affinity and anti-affinity. So these allow you to attract pods to nodes based on labels. The difference with the node selectors versus the affinity is better in the sense that it allows you to have more than just equals. You can have different matching conditions. So you can say something is not in a set of labels, does not exist, is greater than, less than, etc. The nice thing is, as I said with the node label, the node selector, your pod won't get scheduled. So with node affinity, you can be selective on how demanding you are for a particular node. So what I mean by this is, what you can specify is required during scheduling, ignored during execution. You can see developers have named this thing, can't you? This is essentially a hard requirement. So this says that when I select a particular node using this parameter, if it's not available, my pod will not get scheduled. So this is essentially the same as the node selector. Another option is to say preferred during scheduling, ignored during execution. And now this is the soft requirement. So if there isn't a matching thing, it will find somewhere else to run it. Now, if you're looking at this, you're thinking, why have we got all this duplication? There's a lot of words here, a lot of letters. We didn't need all of them. That's because there's a third one. The third one says, required during scheduling, required during execution. So the key difference here is, the first two won't kick a pod off a node if you add a label to it. So they won't suddenly remove it. The required has not been implemented, and actually you can get very similar effects using a different approach, which we'll talk about later. Let's have a look at the YAML for this. So here we have the spec for our deployment, and we have node affinity, and we're saying I want it to be required. So I'm insisting that I have the instance type to be this particular size VM. Okay, so that might be being used for, say, you've got a GPU in some of your nodes in the cluster, and you want to insist that it runs on a GPU-based node. I'm doing an in there. I've only got a single value, but of course, you could have, that's an array. You could have passed multiple values in there. So that was required. Preferred looks very similar, but it's got some extra bits. So now we have this wait. The reason we have a wait is because now we're saying we prefer. There may be multiple nodes that match. So there may be one that doesn't match. Where does it put it? So you can essentially try and influence the behavior, the preference, if you like. So that was node affinity. And so far, what we talked about was pods being put onto specific nodes, if you like. What if a node didn't want a pod to be put on it? This is where you would use taints and tolerations. So a taint allows you to repel nodes. You say, no pods, sorry, let me say that again. A taint allows nodes to repel pods. So what you're saying is, do not put any pods on this node unless they explicitly tolerate this particular taint. I appreciate this can get a bit confusing if you're new to it. But it kind of makes sense once you've used it a little while. You can, to define a taint, you have three parameters now. So you have the key, the value, and then you have the effect. So the effect here says no execute. The effect rather, there's three options. So no schedule says don't schedule it at all. Prefers no schedule says, well, if you're forced to, if there's nothing else, then yes, you can use this node. And then no execute is where this is different. No execute will take pods which are running on a node, and you've just applied a taint to it, it will kick them off that node. It will say, you're not allowed to execute anymore on this node. It's worth remembering that Kubernetes actually adds taints to nodes under certain circumstances. So for example, if that particular node is running out of disk space, Kubernetes will actually taint that node to indicate this, and therefore it should stop or minimize the amount of deployments to that node. And as I mentioned, the key difference here is that you may have a pod running on a node, and if it gets tainted and it's not been tolerated, it will get kicked off. So to taint a node, kube control taint node, give it the name of the node, and this time we pass in key, value, and then colon, and then that effect, so no schedule. So if we take a look at an example where I've tainted one of these nodes, and I've done a deployment that doesn't have a toleration. We can see that we have 3 instances of this particular application, and 2 of them are running on the same node. One is running on 1. There's nothing running on node 0. Node 0 is the one I've tainted. Let's have a look at how I did that. Or let's add a toleration for that particular taint. So now this is my pod spec, and now I'm saying I'm going to tolerate that toleration. That taint is called key name, and the value is that, and then I've said I'm tolerating the effect, no schedule. And with this, it will schedule onto that node. Now this parameter, which I've commented out, is quite confusing, I think. This toleration seconds says that if a taint is applied, you have 3,600 seconds before you will get evicted. If you don't specify, you won't get evicted, as long as you can tolerate the taint. So it's a little bit confusing, in my opinion, anyway. So let's see what the schedule pods now look like now that I've said I've tolerate that taint. And as you'd expect, we're now seeing the pods distributed across all of the nodes. I deleted and redeployed this in case you were wondering. Kubernetes doesn't tend to move pods just for the sake of it, unless it's been forced to by taints tolerations. So just to kind of reiterate, taints versus node affinity. With node affinity, any pod can actually land on a node unless the pod says it doesn't want to. Now, the node has no say in the matter in that situation, whereas the taints work the other way, if you like. They push everything away unless the pod accepts it. So where we use taints is to prevent kind of casual scheduling, if you like, onto certain nodes. So these may be nodes which are expensive or have limited resources. And we'll see an example of this later on when I get to the virtual node stuff, how we use this to power the virtual node. So far we've been talking about pods and nodes and affinity between them. But what if we want to control the effect of pods against other pods? So interpod affinity and anti-affinity, or we normally always call it pod affinity and anti-affinity, they influence the scheduling based on what other pods are running on a node. So this can be useful when you want to control which components run where. So for example, you may want to ensure that a cache is always running alongside an app. Ordinarily, that shouldn't be something you need to do. More typically, you would use it to ensure that your multiple instances of your pods are distributed in such a way they can tolerate an outage of certain nodes, or maybe even a zone, assuming you're deployed across availability zones. So in terms of the way we define them, it's very similar to what we've seen before. We have the same construct, the require during scheduling, ignore during execution. we have this additional parameter called topology key. And this, I have to be honest, is a little bit confusing. Hopefully the next few slides will explain it a little bit better. They reference a level, and that air quotes are very deliberate, a level of your infrastructure to which these rules apply. That level could be host name, could be some kind of failure domain, it could be availability zone. That key is determined by the labels that you've got in your nodes. So when I showed you the labels before, it said availability zone. Those labels indicate where that particular node was running in a particular availability zone. Let's try and visualize this, hopefully make it a little bit clearer. So I've got 4 nodes running in a cluster, and the labels for the nodes say node 1, node 2, node 3. That kind of makes sense. So if I pick the host name label key within the nodes, Kubernetes will treat each one of these as a separate infrastructure, if you like, a separate node, and will use that to distribute the pods. My labels are slightly out. So now imagine that we have a label for those machines where the first 2 are in zone 1 and the next 2 are in zone 2. So this may literally be the case that in the data set, in the region, in your cloud region, they are in 2 different zones. This could be an entirely fabricated label that you've made up for whatever reason. Don't know why you do that, but hey, let's roll with it. So now essentially what you're doing is with the topology key, you're telling Kubernetes to treat them like 2 blocks of servers, if you like. And based on the topology key, it will separate, and the anti-affinity will separate them across that boundary. Is that making sense? No one's nodding, which is slightly worrying, but I'll power on. So here's what the pod spec looks like. Again, the very long-winded attribute. So again, we're saying required here. We're using the label selector. The key thing now is this label selector is picking up labels from our pods. So this is a pod label. Okay, the pod says this component is a cache. And we're saying we want to separate it by host name. So we want the caches to be together with, this particular application wants to be next to wherever there's a cache. It's an affinity. Let's have a look at that in a visualization. So here I've got 3 nodes. I've got 3 replicas of this web and this cache. So with the web, I would specify pod affinity for the cache, and I set that to preferred. The reason that's preferred is because that cache may not be deployed yet. Well, I don't want this to be a hard dependency because otherwise it won't get deployed. The pod anti-affinity is against itself. So what I'm saying is repel yourself across the host names. So that will force the 3 instances of this particular application to go onto 3 individual nodes. Now, that might happen by chance. It sometimes does if there's nothing else going on, but that's how you would force it. So with that, we cause the 3 to be deployed. Now we want to have the cache running alongside. So I'm sure you can probably figure out now that with the cache, we have affinity for the web this time, and we anti-affinity ourselves. And again, we're using the host name, and because of that, we get a nice symmetrical deployment across. I forgot to start my timer, classic. It's fine. So here's the pod spec for the front end. There's a little bit more in there. Can people see that at the back okay? So now we've got the pod anti-affinity. So this is the web one, so we're going to anti-affinity ourselves against the host name, but we're going to have affinity for the cache across the host names. So imagine the cache component. Cache component does the reverse. I won't label the point. What this looks like when you run it, so this is kube control, get pods, I'll wide, and then I've put a label selector. And we can see that I have cache and web node 0, cache and web node 1, cache and web node 2. So you can see there's quite a lot of capabilities around influencing scheduling. Now, if it turns out that none of these do what you want, you press the big red button, the nuclear option, which is custom scheduler. You can write a custom scheduler in any language you want, but it does need access to the API server. Once you've got that, that's the hard bit. Once you've got that, it's actually very easy to use. So in your pods, you would just specify the name of the scheduler. So this will be running in the cluster. It'll be a pod, or hopefully multiple pods, called My Custom Scheduler. So there's an example of this on the web where somebody's implemented a scheduler using Bash. Pretty sure that's not production ready, but worth mentioning. Okay, so we talked about influencing scheduling. That's fine. What if we need to get more control? What if we want to start extending Kubernetes? What if we want to have control over the resources that are created within our cluster? We maybe have some custom policies that all resources must adhere to a particular standard. So, for example, you might say they must all have a label, or they must all have resource limits applied, something like that. You might want to prevent certain resources from being created in the first place. You might be using ingress for everything, and you don't want people to create load balancers. Or you might want to inject additional logic when a resource is created. So we'll talk about a little bit later, things like Istio, they inject their sidecar using this kind of approach. To do this, we use something called admission controllers. So essentially, this is code that intercepts the request that you make to the API server, and you can do something with it before it gets persisted. There are a variety of controllers available. Controllers can be validating. So this means they will inspect the object. So this is where you might say, you must have a label, otherwise I'll reject your deployment. There could be mutating. Mutating means they'll change the objects. So here you might say, well, you didn't specify a label, so I will put a label on there. You know, team equals idiots or something. Don't do that, it's rude. Finally, controllers can be both. Admission controllers can be both. It can be both mutating and validating. Admission controllers are part of Kube API server. They get enabled or disabled as part of Kube API server. So if you're in the previous talk, and I'm sure you know if you're running managed Kubernetes providers, then you don't have access to Kube API server. You can't set some of these flags. The other problem with them is they're compiled into the API server binary. So if you want to create your own, you're going to have to fork Kubernetes and modify it. Good luck keeping that one up to date. So there's actually a number of admission controllers built into Kubernetes. And now I'll talk about them in detail. No, I won't. I'm not going to talk about these in great detail. I think the key thing here is you need to check with your particular cloud provider to see if they enable the admission controllers you expect or you need. Let's have a look at the lifecycle of a request, an API request, and where these controllers fit in. So I make a request to the API, and it hits the HTTP handler. The handler just does the authorization and authentication checks. It passes it to the mutating admission controllers. So these are the things that may modify that request. Those modifications and the original request are validated against the object schema. So you're trying to do something, you're trying to create something that doesn't exist. Now the validating ones can kick in. So the custom validating ones, if you like. Now the reason why the validating ones come at the end, or after the mutating ones, is obviously you could bypass the object schema validation by mutating things if you didn't do it that way around. And finally, that request, that resource is persisted into etcd, and then the rest of that process kicks in. The controllers for that particular resource kick in, and they start doing what they need to do. Now, if we want to have some custom logic, instead of having to compile API server ourselves and add our own logic to it, there are two special admission controllers that we can use. They're called, and they're a bit of a mouthful, mutating admission webhooks, and validating admission webhooks. As far as I know, all of the main cloud providers have enabled these particular admission controllers. And they're pretty cool because they allow us to do some extensibility without modifying API server. So the mutating admission webhook allows you to modify resources or create new resources when an API request comes in. And as the validating one, as the name suggests, it allows you to validate it and potentially block an API request if it doesn't meet your particular requirements. The nice thing with these are, they're webhooks, web standard webhooks. So therefore, they're just going to invoke a HTTP callback, and the logic for that callback can live anywhere you want it to. It can be inside the cluster, it can be outside the cluster. So let's have a quick look at an admission webhook. So this is the configuration for an admission webhook. This is the YAML. Can everyone see that at the back okay? Yep, thumbs up, cool. So API version, again, people are very familiar with this. The resource kind is a bit of a mouthful, validating webhook configuration. Metadata is the name, and then I give it some unique name. So normally it's a URL for your company or something. And here what I'm saying is, these rules apply, the Visual Studio Code not helpfully is popping things in the way. Let me do this. API version 1, and on create operations for pods, I have this failure policy. Essentially what failure policy says, if the webhook fails for some reason, this might be technical reason, then fail, essentially it's a fail safe. If there's a technical reason why the webhook doesn't fire, you fail, you treat it as a failure. And here's the interesting bit. So here now we're saying we call, client config, and you see the URL is pointing to Azure Websites API. So what I'm doing here is I'm actually invoking a webhook, a validation webhook into Azure Functions. So let's have a look at that webhook, the Azure Functions code. So this is an Azure Functions code. I just used the Node.js example. I adapted one from Kelsey Hightower. So the stuff at the top you'll all recognize if you do Azure Functions already. I just log some messages. I get the request out of the body of the request. You dig a little bit deeper to get the pod. And then what I'm doing is if there's, this is a response it expects, so I'm going to set that up as a failure first, and then I'm looking at all the containers within that pod spec. So remember, you can have more than one container within a pod spec, so I'm looping through the containers. And in this contrived example, what I'm saying is, if the image, so I'm saying this image, which some of you saw in the last demo, is a bad image. We know it's a bad image, and we don't want to use it. Now, this is a contrived example. There are better ways of doing this, I suspect. But what I say is, if the image is this one, then I'm going to basically log a message saying it's a bad image, and I'm going to send a response back saying it's a failure, and I'm going to say this container image is a bad image, and the reason it's not allowed, and a 402 status code. Anything else just goes back as an allowed equals true, and that gets sent back as an admission review. So that's what 48 if you include the braces, lines of code. So let's go to the portal where I'm running this. Oops. Just make sure I'm connected, so let me just clear that. So this is the Azure function. I've just popped the console up. You don't need to view this in the console, but let's try it. So now in my cluster, I'm going to apply that webhook we just saw earlier. So okay, apply. That webhook's now been deployed. So now if I try and create the pod, and what have I called it? Hello world. Yeah. So if I now do k apply -f v1, and I run that, cold start, Azure functions, well, all functions, we can see now we got an error. Error from the server, image not allowed, error when creating, blah, 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 blah. If I come over to the function, and yes, we didn't see clearly didn't connect properly. It's annoying. Take my word for it, it did actually invoke that function. What we can do is we can do k, get events, and we should see somewhere. I thought you could see it, but maybe you can't. So just to prove that it's not kind of smoke and mirrors, let me try and apply the V2 pod. So this is now using the image, the V2 image. I can show you the pod spec just to prove the point. So there's the one, here's the one using the 2. And that one gets created. So we see that's running. So that was the webhook being invoked through the Azure function. Now I chose validating because validating is a lot easier to write. Admissions a little bit harder, but you'll find examples if you're looking to do this. Let's go back to the slides. Half an hour in. So far we've seen influencing the scheduling. Now we can use these webhooks to influence what gets created, and whenever a request comes in. What if we need to go further? What if we need to create even more customizations, if you like? We have an option to extend the Kubernetes API. We can actually build abstractions on top of the Kubernetes resources. In fact, we can create totally custom resources and treat them as if they were Kubernetes resources using the same commands that you're familiar with using with kubectl. Now, if you want to extend Kubernetes API, you have a few options. The first one is to create an extension API server. Now, this is quite hard, because you have to essentially implement an API server from scratch. And then you can aggregate that along with the existing API server. And this was the only option in the past. Another option is to use custom resource definitions. Now, this is the thing that most of you here who are familiar with Kubernetes will have heard of already. Then we have custom controllers. Now, often, custom resource definitions and custom controllers are bundled as one, or they're conflated. So we'll say it's a CRD when actually we're not talking about a CRD. So let's talk about CRDs more specifically. So this is a new resource type that will sit alongside the existing resources within Kubernetes. And just to clarify, by resources, I mean pods, deployments, services, ingress, et cetera, What we can do is we can use kubectl to create these, to delete these, to manage these like we would. These custom resource definitions are persisted in etcd, so we don't need to bring our own persistence. With the API servers, we would have to write our own, we'd have to use our own persistence as well. The key thing with CRDs, custom resource definitions, is they are pretty much useless without a controller to act on the resource. So let's have a look at a custom resource definition. So again, familiar looking YAML. So we've now got a custom resource definition. I've got some metadata for it. It lives in a group, an API group called test.example.com, version 1. You'll see where that kicks in later. This particular custom resource definition is scoped to the namespaces. You can have a cluster-wide one as well. And then this thing is called foos as a plural, singular is a foo, and it's a resource kind of foo. And I've also specified a short name, FO, like you would in get PO, get pods, and get SVC instead of get services. So once I've created that custom resource definition, I can then create an instance of that resource. So now, just like my pods, my deployment manifest or my pod spec would look like, I say API version. Now that's the API group I specified earlier. Here's my resource kind, foo, metadata I can put wherever I want, and then the spec I can put wherever I want. That's the information that I will get in the controller if I build a controller for this. As I said, by themselves, these are useless, but you can go and do this now. Let's have a quick look at an example. So I think this is a little video just showing you the basics. So I can apply that cube custom resource definition, and it tells me it's created that. Now I've got a resource called foos. That was the same YAML files I just showed you, actually. Now I can do kube control get foo. That's not built in, is it? In fact, I can get kube control get fo. And I can see that object I just created. Then I can delete it. That's pretty much all I can do. So actually, it's pretty useless. I've just done a little bit of a CRUD operation. Don't use etcd as a database and do this way of storing records, please. So you need a custom controller. So custom controllers allow you to extend or change the behavior of resources. Now, we often talk about, and I've literally made the mistake of saying, you need a custom controller for a custom resource. You do, but custom controller can actually operate on existing resources. So you can have your own custom controller that does something totally different when a pod is created. They're often paired with custom resource definitions because they're the things that actually power the custom resource definitions. They are very often implemented in Go. In fact, I don't know of any official ones or any in production ones that aren't implemented in Go. I don't think that's a hard limit. You can actually use other client libraries. It's just custom controllers have to use the API, machinery, client Go library, and it gets a little bit gnarly. This is not a topic for, in great detail, it's not a topic for a talk. This is a workshop, and there are companies who do workshops on extending Kubernetes. You often hear the term operator, and essentially what an operator is the combination of a custom resource definition and the controller that goes with it. So before you run away and kind of start creating your own operators, it's worth knowing that there's a hub of operators in the wild there. The text is a little bit small, but I mean that's all the A's. So there's an AWS one, for example. So the AWS operator allows you to basically interact with AWS resources through Kubernetes. So you can find more there. One of the things that makes writing operators slightly easier is using something like the operator framework. So this was created by the Core OS team, I believe, at the time. And it's not easy by any stretch of the imagination, but it does a lot of the plumbing. So it does a lot of the templating for you that you might need. There's a operator within the Kubernetes documentation as an example. That's probably a good place to start looking at this as well. If you're really interested in writing operators, I would encourage you to also look at your language of choice, see if there's a client library. Chances are it's an unloved client, and maybe help bring that one up as well. Go is awesome, but it's always good to get other languages working in these things as well. So we're going to take a bit of a shift now. We're going to shift on to scaling. Now, there's another talk tomorrow by Lewis, who's going to dive a lot deeper into scaling than I am. But I wanted to show you one particular feature that you may have come across or heard about, particularly more recently, that I wanted to demonstrate. So when we talk about scaling, we have horizontal pod autoscaler. Pretty sure everyone here has heard of this. So essentially, this allows you to scale the number of pods based on metrics. There's a V2 HPA, which is actually quite nice because it allows you to scale based on external metrics. So you can pull in metrics from some other service and scale your application. And if you were following the build news, Microsoft open sourced a project called KEDA, which allows you to scale resources down to 0 and then wake them back up when a request comes in, which is pretty cool because you can't ordinarily scale down to 0. We have the one that's probably not so well known, the vertical pod autoscaler. So essentially, this increases the amount of resources that are given to a pod when it needs to scale up. So obviously, one is scaling out, this one is scaling up. Then the third option here, we have the cluster autoscaler. So the cluster autoscaler will scale the number of nodes within your cluster. And the way it does this, it determines if there are pods waiting to be scheduled. And essentially, that's a trigger that there are pods that cannot be scheduled because there's not enough resources, and it will trigger an autoscale. Now, the autoscale it triggers depends on your cloud provider. if you're running in AWS, this is what scale groups, I think they call them. In Azure, this is in AKS in preview. It uses the VM scale sets. The problem with scaling your cluster is that takes time. It might take a minute. It might take 3 or 4 minutes. Let's be realistic. It'll take 4 or 5 minutes. What if your load is very spiky and 4 or 5 minutes is just too slow? We now have this additional option, and it's called a virtual node, virtual kubelet / virtual node. I'll try and clarify the terminology in the next slide. So this is an open source project. It was actually originally created by the Microsoft team, and it's now it's part of the CNCF. They donated it. Essentially, it allows you to connect some external compute resource into Kubernetes and make it appear as if it's another node in your cluster. The key difference is this node may have infinite capacity. So kind of how this works is within my cluster, I have 3 real nodes, if you like, whether they're VMs or bare metal. I deploy the virtual kubelet is the technology that powers the virtual node. So through that, we create this node. It looks like another node, but it exposes the same kind of functionality you'd expect from a node. So you can treat pods, deal with pods on that node. You can also call some of the node functionality. The key thing is when you schedule something on this node, it actually gets scheduled or put onto whatever the backing compute provider is. So there are a number of these providers. Azure Container Instances, ACI, is the serverless container offering from Microsoft. Fargate is roughly the equivalent. And then there's various implementations, HashiCorp, Service Fabric Mesh, and then IoT Edge. This actually went, they announced it publicly yesterday, I think, or the day before. Now they're using this to essentially allow you to run IoT Edge on an on-prem Kubernetes cluster for IoT purposes. So quickly touch on Azure Container Instances for those who are not familiar with it. As I said, this is serverless containers, so we're trying to get all the buzzwords in here. The key thing is there's no infrastructure required. To run a container, I would do, from the command line, I do AZ container, create, give it the name of the container, and pretty much that's all I need to do. And that container will be up and running within usually seconds. The key thing is you pay per second for the billing of that. You stop the container, you stop paying. And as of about a month ago, the pricing on ACI was cut dramatically. It's now very, very similar to running the equivalent-sized server on Azure Web Apps, for example. So this is really quite good when you're testing images for short-lived containers, and the bit that's interesting is for bursting, for sudden spikes. So you see where I might be going with this. So if I take my virtual kubelet, my virtual node, if you like, and in my cluster, I use the ACI provider, then my cluster is running, and suddenly I get a spike in traffic. The cluster gets hot. Because of that virtual kubelet, containers can actually start overflowing into ACI. And because ACI is essentially unlimited in the resource, it can continue to take that load, and potentially in the meantime, I might be scaling my cluster if I think this is an ongoing load. If you want to enable the virtual node in AKS, it's just a tick box. It's just down there, enabled. Let's have a look at this as a demo. This one, I think I'm going to use a video just because it shows it a bit clearer, I think. And I'll remember to show the video this time. So what I've got here is a Kubernetes AKS cluster, and I've got the virtual node enabled. See if I can. So I've got, see there, I've got 3 nodes, and I've got this ACI node. The 4th one there is a Linux one. You can see it says VK there. If I describe that particular node, the virtual node, we see a load of stuff. Interesting here is if you look, doesn't really matter. You've got some labels, and you can see, whoops, I'll get rid of that. It's just in the way. You can see that it has, key thing here is it's got a taint. So we're tainting this virtual node. We're saying don't schedule anything on this virtual node. And that kind of makes sense. Let me pause that a second just to drive that point home. I'll come back a second. So we're tainting it. So come back to what I started with. We're saying don't schedule on this node accidentally. And the reason for that is we're going to pay for Azure Container Instances. If we have capacity in our cluster already, why would we want to put, if we don't specify that, then Kubernetes may well schedule on there, especially when you see that it has 4 terabytes of RAM, apparently. Just out of shot there, but it has 4 terabytes of RAM. Some crazy numbers they use. So we have this node, but it won't get scheduled by default. So now I've got a sample application, which is like a web application. It's like an e-commerce application, if you like. And for some insane reason, I'm running only a single instance of it. But hey, let's not worry about that. If I get the pods in now, we can see that it's running on one of the actual nodes. There's nothing running on the virtual node. You can see that there. If I look at the, that particular pod, if I look at some of the details on it, what we'll see is that it has a toleration, slightly too fast. Couldn't find it. We can see there it has a toleration for ACI, for that virtual node. So at this point you're thinking, well, why isn't it being scheduled on there then? And the reason it doesn't get scheduled on there is because although we've said we tolerate that node, what we can now do is use node anti-affinity and say we prefer not to run on that node. So now what we're saying is, I've got that node, I can use it, but I'd rather you didn't unless you really had to. So let's go to the app. It's like a web app, and I've been busy buying. You can't see this. My laptop screen is flickering really badly. I've got a Surface, and it's dying. So I do need another one of these. Unfortunately, this one doesn't really ship anything. So there's about $13,000 in the basket there, I think. So let's imagine there's a sudden spike in traffic. So here, this is the AKS running. And let me just pause this, I think, because I'm going to probably talk too slowly. And what we can see is this is the metrics coming from AKS. So if you haven't used AKS and seen the metrics, it's quite nice. We can see the metrics. I think this application is a combination of Node.js and various other things, actually. It's not necessarily .NET. We can see we've got pretty much hardly any requests coming in. Our request latency is something like 1 millisecond or something I can't quite see on my screen. And that's because there's nothing running. So what I'm going to do now, in the Cloud Shell at the bottom here, I'm going to run, what am I going to do now? I'm going to set up this demo. So over this side now, I'm starting to run a load test. I'm using this tool called Hey, which is really cool. Very easy to start doing load testing. So if you look up there now, you'll see a massive spike. So we went from 0 to 200 requests per second. And initially, we're seeing a little increase in our latency. So our request duration has gone up to 500 milliseconds. Now, if we keep an eye on that, and on the left-hand pane, if I now do get pods on that store pod, we can see there are a lot more pods. We can see more pods are being created. So we're now scaling. And we were scaling in that time. That's real time. I haven't chopped that video or anything. That's how long it took to start scaling. Now, if we look at the where these pods are running, I now do get pods. So I'm going to filter specifically to the online pods, and I'm going to look at where they're running. So you can see they're all running. All the other pods are running on the virtual node. So now these are spun off. They're running on ACI. I'm paying for these containers, paying fractions of a penny at the moment, probably fractions of a penny. And now if you notice, that load came back down again. That request time actually came down, even though the load is continuing to go up. The request time has actually come down now. We're almost bottomed on there, some of them. So now if I kill that load, what happens now is this, it takes about 60 to 90 seconds to cool down. Now, I didn't want to wait 60 to 90 seconds. That's an awful long time when you're standing up on stage. So I've chopped the video, but when I do get pods again, after that 90 seconds or so, we can see we're now back to that pod that was running on our actual node. So that load disappeared. We stopped paying for all those containers on ACI. There are no more containers running on ACI. And we're now back to where we were. I'm going to do that again, just the first bit, just to show how quickly it scales. So just kick the load off. And we can see, so that was what, 5, 6 seconds, nothing yet. I do that one more time. How long has it been now? 15 seconds maybe? I don't know. Time is relative. There we are. We're starting to see it scaling. So that's how quick it scales. We're not going to watch that again. I just thought I'll show it again just in case you missed it the first time. So we have about 10 minutes. So I want to quickly recap what we saw there, because we brought together some of the things I talked about earlier, and it's worth just reiterating for anyone who, just to make it a little bit clearer. So that virtual node, we tainted it to prevent accidental scheduling, because that will cost us money for no reason. Then the e-commerce deployment, we said we want to tolerate that taint, and we put an anti-affinity to prevent it being put on there unless it needed to. So hopefully that kind of explains that concept. The virtual node is really cool. You can imagine where we may be going with virtual nodes in terms of serverless, all the things. I want to do a bit of a crunching gear change at this point and talk about service-to-service communications. Now, I'm not going to spend too long on this because I've done a talk previously where I go into a lot more detail, and I think there may be a talk here. If not, there's nearly always another talk on service meshes at these kinds of events. So I didn't want to overlap too much. So the key reason why we need things like service meshes is because the built-in offerings in Kubernetes are a little bit light. So we have pod security policies, which allow us to control what pods can access which other things. We have network policies, and we have ingress. The ingress in particular is very light. It allows you to do path-based routing, host-based routing, but it doesn't let you do anything else. When we want to do traffic shifting, traffic management, it allows us to power lots of different scenarios. So it allows us to do canary deployments. We can't really do canary deployments very easily in the built-in stuff within Kubernetes. It allows us to do A/B testing. We can deploy 2 versions, and we can test the different responses we get. We can do the thing I really think is very cool. We can launch our application darkly. And what this means is we can deploy our application into production, and it can experience production load without actually ever being visible to the users. The way this works is the traffic is actually mirrored by the service mesh and sent to your existing application and also sent to your new application. This is a really powerful way of understanding how your application is going to behave in production before you actually launch it to your users. We all know that testing anywhere else is not quite as good as production. And as I kind of touched on in the previous talk as well, we can use traffic routing to access legacy and cloud-native applications. Most of the service meshes have the ability to also run on VMs, Linux VMs typically, and you can also then essentially bring them into a service mesh. So I mentioned service mesh a couple of times, probably worth just clarifying what service mesh is. So this is a quote from Buoyant, and it says, service mesh is dedicated infrastructure for handling service-to-service communications. The key thing is when we talk about microservices in cloud native, we've gone from having applications which are making in-memory function calls to now making network calls. And if you're familiar with the fallacies of distributed computing, we say the network is not, we say the network is reliable. Of course, it's not reliable. So one of the most well-known service meshes, the one that probably most people have heard of, is Istio. So Istio is an open source project being led by Google, Lyft, and IBM. It's essentially a Google product. I think most of the engineers are from Google. I might be wrong on that, but I believe that's the case. It's not currently a CNCF project. So it's not currently donated to CNCF, and this is probably why I've not heard anybody from Microsoft in a formal capacity mention it. And in fact, AWS have recently launched the App Mesh, which is their service mesh offering. So it runs on top of Kubernetes and actually other platforms as well, and it extends the capabilities. Now, we've talked about how we extend Kubernetes, and that's exactly what Istio does. It uses custom resource definitions, custom controllers to do that. So the features it provides gives you network error handling and retry logic and circuit breakers and all those things. Now, we're .NET developers, and most of us are, and we're probably used to libraries like Poly, and you're wondering, why would I need this thing if I've got Poly? Service mesh has pushed this concern down to the infrastructure layer, if you like. It was software-defined infrastructure, but it's still infrastructure. So our applications don't need to have that particular library, and essentially, if you imagine if you had a bug in Poly, you would have to redeploy all your applications that used Poly to fix that bug, whereas here you would patch the actual service mesh. The other thing with that is obviously if you're using different language, you have to implement the same logic in another language, and there may be differences. Istio allows you to do rate limiting. So if you've got a service that's misbehaving, or you just need to control the downstream effect, the herding effect, you can apply rate limiting. It allows you to do traffic shifting and mirroring. Mirroring is what you use for that launching darkly. This is what allows you to send subsets of traffic based on any of the layer 7 values. So this could be header values, this could be percentage of traffic. It allows you to inject faults. So when we're doing distributed applications, we need to test faults, and it becomes a lot more difficult. So with Istio, we can inject faults in a very consistent, reliable manner. You can also use fault injection and traffic shifting to prank your colleagues by making sure that certain colleagues always get the same fault and no one else does. But yeah. So things like Istio allow you to secure service-to-service communications. So they will encrypt the traffic, and they will apply policies that prevent certain pods from talking to other pods. And finally, they allow you to have some visibility of the requests and where they've been going, the distributed tracing. So I said, if you want to see more on some of these as an example, the video I'll link to at the end will show that. So just to wrap it up, so there are many constructs within Kubernetes that let you control the pod scheduling. And these admission webhooks are a nice, I think, very accessible way of doing some extensions without needing to go too far. And of course, when you need to, you have that control. Again, where I think Kubernetes is so fantastic is we've got so many options, and then we can still extend it further if we want to as well. And then this virtual node, I think, is very cool, because we're probably heading towards a place where we will have serverless Kubernetes. So if we're on a managed Kubernetes provider, we don't have the master nodes to deal with anyway. And now if our VMs all become virtual nodes, then we have no infrastructure to manage as part of Kubernetes. So that's pretty cool. If you want to learn more, that auto-scaling example I showed you is at that GitHub repo up there. This is that video I linked to. I mentioned it from Sydney last year. And then Katacoda. How many people here have heard of Katacoda? Okay, but still only a handful of people. So Katacoda is an online learning platform where you can go and play around with nearly every cloud-native technology you can think of for real in a browser. So you don't need to install it in a local machine. You just need an internet connection and a browser, a modern browser, so no IE6 or anything, please. And you can go and have a look. So there's an OpenShift course on operator framework. There's Kubernetes basics. There's Istio details in there. There's OpenShift. There's every technology you can probably think of that is current is available. And what you get is instructions on the left-hand side and a pane into a real cluster. So you're seeing some real machines there. It's not a fake console. It's real. So with that, I think I've got probably 30 seconds to go. So I'm happy to take questions as I pack up. Otherwise, I say thank you very much. And that's me.